Hey everybody, I hope you're doing all right today. Today we're going to talk a little bit more about the pendulum. Okay, so what can we say about the pendulum? Well, we did an experiment last week where we looked at how the pendulum's period was related to its length, right? Okay, so let's talk about that. So, what were the factors that influenced the motion of a pendulum? Well, the one thing that we did a couple of things, of course, but one thing that we did was we took the time for 10 swings. Do you know why we did that? We took the time for 10 swings so that we could be a little more accurate. Remember, getting the time for one swing is actually kind of difficult. So if we get the time for 10 swings, we can minimize the amount of reaction time error because we have a lot more time, and then the amount of reaction time in starting and stopping our stopwatch becomes small compared to the total time. So in general, it just makes it more accurate for us. So mostly what you did was you varied the length of the pendulum, and you saw how the time changed, in some cases dramatically. Then you made a graph of that. Okay, now what are the other things that could affect it? Does the mass matter? Does the angle matter? Well, the mass does not really matter significantly. I don't know if we did this in class or not, maybe not, but we will show this soon, if not, that the mass makes basically no difference at all. That is to say that regardless of the mass of the pendulum ball, the ball part, as long as it's way more massive than the string, the mass doesn't matter as long as all the mass is concentrated where the pendulum bob is. Now, what about the angle? Well, the angle makes a small difference. It's a measurable difference. It's a pretty small difference, but if you keep the angle very low, like within, if that's vertical, within about 15 degrees of vertical, if you can keep that very small, then the angle makes an almost insignificant difference. But even if you make the angle bigger, it only makes just a few percent of a difference. But that's measurable. Still, so the angle matters a little bit. Again, mass? No. Length? Definitely. And the angle? A little bit. We'll come back to the angle just a little bit later. But for now, it does not matter. Okay, now what did our graph look like? Well, the graph looked kind of like this. It was sort of swooped over when you graphed period on the vertical or y-axis versus the length on the horizontal axis. You got something that looked kind of like that. And that doesn't look much like a graph you've probably seen before, unless you've ever seen one of these. Now, if you've ever seen a graph like this is called a parabola. And a parabola means that the y, vertical, is proportional to x, to some exponent, and usually we start off with x squared. And in fact, that graph looks kind of like it, but only if you turn it on its side. So let's take a look at that. So there's our graph, swooping over, but if you turn it on its side, then you see that, yeah, sure enough, that looks a lot like a parabola. And in fact, that is actually the case. So the length is now on the vertical axis, on the y-axis, and the time is now on the x-axis. It's flipped from what it was. So that means the length is proportional to the time squared. If it's a parabola, we can test this. If it's a parabola, the length is proportional to the time squared. Another way of saying that is that the time is proportional to the square root of length. What I did was I actually took the square root of both the length and the time squared. The square root of time squared is time, and the square root of length is just square root of length. Now, when you do that, you start to see what this formula looks like. And that is it. That is the formula for the period of a simple pendulum. So definitely there are a few details that are skipped here, but you can start to see from our experiment how there is a square root relationship. Okay, so this is the formula for the period of a pendulum. What we're going to do is use this formula and predict how long it takes any pendulum to make one complete swing. And I think you'll be impressed just how well it works. So, the period of a pendulum is given by this relationship. 2 pi times the square root of L over G. That is, T equals 2 pi times the square root of L over G. So what's T? Well, T is time, or period of one complete swing. That is, from the start, over, and back. That's a complete swing, or a complete oscillation. 2 and pi, numbers. They're constants, they're numbers. 2 is just 2. Pi is 3.14159. We usually just cut it off at 3.14. Now, the symbol that you see there is a square root, which is the opposite of squared. So you can do that on a calculator. Use the square root button. It's usually second x squared. And then inside the square root symbol, you have got L length divided by G. Now, G is something brand new. It is gravity. G is the rate of gravitational acceleration. What that means is, if you have a freely falling body, a body that's just free to drop, it picks up a certain amount of speed with every second of free fall. That amount, near the surface of the Earth, is about 9.8 meters per second. So, now the pendulum isn't exactly in free fall. It's suspended by a chain, but clearly the period is related somehow to gravity. And this value can be shown with experiment as being 9.8 meters per second. So that's the value that we happen to use if we are near the surface of the Earth. Now, if we were on the moon, G, what do you think G is? If you're on the moon, is gravity more? Is it less? Well, you're probably not too surprised to learn that gravity is significantly less on the moon. It's actually about 1/6 that of Earth gravity, so it works out to be about 1.63 meters per second. What that means is that a pendulum takes a lot longer to make a complete swing on the moon. Which means that the period, of course, goes up. All right, so let us try a simple problem. Now, here's the formula. In front of the room, we had a bowling ball pendulum hanging, which I don't know if you've seen that yet, but you will soon. So this pendulum is about 3.2 meters in length. We measured it in class. And how long then will it take to complete one swing? Well, you just have to use the formula for T equals 2 pi root L over G. Let's see how you do that. There it is. We're plugging numbers in now. L is 3.2 and G is 9.8. So, math. 2 times pi is equal to 6.28. That's 2 times 3.14. And then you get the square root of, well, what's 3.2 divided by 9.8? That works out to be about 0.326. Through 6.28 times the square root of 0.326, that's when you have to do it on a calculator, and you end up with 6.28 times 0.57, and then when you work that out, you got 3.59 seconds, about 3.6 seconds. And sure enough, that is almost exactly what we come up with when we do it experimentally in the classroom. So the formula works. This tells us a couple things. This tells you, well, the formula seems to work. It also might suggest to you that we measured the length pretty well. I measured it, and maybe I did a good job. I thought it was plus or minus a centimeter. And what else does it say? It says that this formula's got real predictive power. Okay, so what I want you to do is, I want you to try one on your own. So I want you to imagine that you have a 2-meter long pendulum. How long will it take to complete one swing? Remember, pi is going to be 3.14. G is 9.8. Now, you can stop the video at this point and try it. Although I have to confess, I'm going to give you the answer here in just a minute, but I'm not going to show you how to do it. So, again, I would stop the video, or not, and then you can see what the answer happens to be here. You definitely want to work toward the answer if you didn't get it the first time. Okay, are you going to stop it? Maybe? Maybe? All right, well, if you didn't, there's the answer. You should get about 2.8 seconds for a 2-meter long pendulum. All right, friends, that's how it works. So, what should we remember? Well, a few things we should remember about the pendulum. The mass does not matter. The length really matters. And the angle matters just a little bit. But if you look at the formula, you can see neither mass nor angle are in it. So it doesn't matter much unless you choose big angles. And then, as it turns out, the formula becomes modified a little bit. It's a little bit more complex. If you're really interested, go to the Wikipedia page on the pendulum, and you can see the actual formula for the bigger angle pendulum. And G is this value of gravity, which near the Earth's surface is about 9.8 meters per second. And if we did it somewhere else, like on the moon, it would be less. If we did it on Mars, G is about 3.9 meters per second. If you could do it on Jupiter, it's almost 25 or 24, but You couldn't really do it on junior. Okay, friends, that's all I have for today, and good luck.